Okay, so I guess, yeah, welcome everyone. Yeah, so very happy to have Keaton Hamm speaking this week. So Keaton did his PhD at Texas A&M. Um, he then, so then you were a postdoc at University of Arizona, and I think, and also an assistant professor at Vanderbilt, and okay, currently back at University of Texas at Arlington as an assistant professor. Okay, so very happy to have you speak this week. And you're going to be talking on manifold learning in Wasserstein space. So if you have any questions for Keaton, please feel free to either unmute yourselves and shout out the question, or I'll monitor the chat and I'm happy to interrupt Keaton as the talk goes on. So thank you very much, Keaton, and over to you.
All right, thank you. So thank you for the invitation to give this talk, and thank you all for attending it or watching it online. So as Matt said, I'm going to talk about manifold learning in Wasserstein space. So both of these ideas are today sort of well explored, especially in machine learning. And I'm going to kind of talk about how these two topics are joined and give some sort of indication of some theory that we've developed and as well as some potential applications. So first of all, this is joint work with a number of collaborators shown here. And I'd like to thank the support from NSF and the Army Research Office as well. So my starting point is that, you know, many applications we get data from these days, especially maybe more sort of tech industry driven. So maybe in computer vision, we get a lot of imaging data or video data from different recordings or NLP data from document corpus. These are all very high dimensional, right? And but there's this notion that's sort of been well understood for a while that even though ostensibly this data that we're obtaining is very high dimensional, it often exhibits some sort of low dimensional structure in it. So it's not typical. It's not always true that we just have some, you know, huge point cloud that really fills out sort of my ambient high dimensional data space. Often there's something more underlying it that we can utilize and explore. Okay. And so, you know, this sort of begs the question, if we sort of know this from practice and experimentation and even theory, what does this mean for us? Right. And there are a few different things. So one could be, you know, I may want to build methods to detect these structures, right? So that I can tell if they exist in my data and therefore exploit them. Often we would want to learn these structures. So by that, I mean learn sort of the features necessary to describe whatever the structure it is. So for instance, if I know that my data is concentrated near a subspace in Euclidean space, I might want to learn a basis for that subspace. Or what we'll talk about a little bit today is if my data is concentrated on or near a manifold, I might want to learn some features of that manifold, like charts or tangent spaces, or some sort of embedding for the manifold. And the other one is that if we have this structure, we often would want to utilize it in some way. And particularly what has been explored in this area quite a bit is, you know, if I have a low dimensional structure in my data and I want to run some sort of learning algorithm or do some sort of inference or, you know, some computational method, oftentimes the complexity of those algorithms is could be polynomial or at worst exponential in the high dimensional data space. But you can design algorithms that use these low dimensional structures where the complexity is then governed by the low dimension of that manifold or subspace, for example. So if I have a two-dimensional manifold in million dimensional space, it's a huge cost savings if I'm able to design an algorithm that takes that manifold structure, and then the computational complexity is, you know, the number of data points squared instead of to the million. Okay, so this is one way that this is utilized in practice. So I want to give a brief example here, just as a motivation, of one task that we might want to do. So this is sort of, you know, now classical in machine learning. We have these handwritten data sets, right, of digits or letters or different things. And one thing that I might want to do is, you know, suppose I have some sort of like idealized zero. Okay, so I'm a little squiggly here writing on my tablet, but pretend this is a ideal zero. And then many other people write down their zeros, and they may look a little different, right? So I may have some like this, some rotation, maybe some scaling, something like that, maybe some little deformations, whatever, right? So my data set is here on the right. So these are my data. And then this is some sort of ideal. And in order to understand the structure of my data set, one thing I could do is to try to find some sort of compact representation of the types of deformations that transform my idealized zero into the actual data that I have. So maybe I look for some set of transformations governed by some parameter set theta, such that I can take this idealized zero, transform it, deform it in a certain way, and get what's on the right-hand side. So here, my parameter theta is going to be in some global parameter set I'll call capital theta. And, you know, best case scenario, I can realize this as some subset of RD for some low dimension D. So D is small here. Right, so if I want to understand my image data set, I'd like to transform that problem into understanding some sort of parameterization of maybe diffeomorphisms that get me from this idealized zero. So this is sort of an example where you could try to find this sort of structure. So here, the thing that we would be interested in is this sort of compact parameterization of my data. Okay. So we'll assume today the manifold hypothesis. This is fairly common, and that is it is the beginning point of manifold learning. Now I want to give some different viewpoints of this. So typically, most commonly, our data we treat as coming from Euclidean space. And so in the Euclidean setting, the manifold hypothesis just says my data is in some high dimensional Euclidean space, R capital D, but really it is concentrated on or near a low dimensional manifold that's embedded in the high dimensional space. So here you have a two-dimensional Swiss roll embedded in R3, or you may have this one-dimensional spiral that is embedded in R2, but then the blue points here are noisy samples of this spiral, okay? But what I'm going to do today is I'm going to change this a little bit and use what I'll call a functional manifold hypothesis. I use functional here in the more machine learning sense rather than the mathematical sense. But so what the assumption here is that the manifold is actually in some more arbitrary space. So it could be a function space like Hilbert space, Banach space. So pick kind of your favorite thing to visualize here. It could be Sobolev space or something with regularity. So we'll sort of take that viewpoint that we're not dealing with simply Euclidean data, but something in some infinite dimensional space. But actually, I'm gonna focus in on a very particular case of this today, and that is I'm going to assume that my manifold is inside Wasserstein space, the quadratic Wasserstein space on Rn for some n. So briefly, this is the set of probability measures on Rn with finite second moment. And I'll come back more to describe Wasserstein space in a moment. But I'm going to talk more about the manifold learning pipeline that I have in mind first. Okay. And I guess maybe I should say here, the reason for this hypothesis is that, well, actually, sorry. So I have some illustrations here in a few slides, so I'll let it wait till then. So my goal for manifold learning in this case is going to be, I want to find an embedding of the data manifold into low dimensional space. And in this case, we will embed into Euclidean space. My embedding can be linear or nonlinear. Largely, this talk will be focused on nonlinear embeddings. And when I find such an embedding, typically I want to preserve some sort of structure of the underlying data manifold. And in this case, I'm going to ask to preserve the geodesics. Okay, so I'm going to assume that my manifold is nice enough that I have geodesics between every point. And this is what I want to preserve. So I'll illustrate this in a moment. There are some assumptions here. But for now, think of, like a smooth Riemannian manifold, kind of as nice of a manifold as you want for the purpose of the theory. So I'll assume that I'm given so I have a manifold of dimension D embedded in Wasserstein space, and I will assume that I'm given n data points from this manifold. So each of my data points is now a probability measure. Okay. And then my goal will be to find some mapping phi that sends Wasserstein space into some Euclidean space Rk. And the assumption I will make is that K is at least the size of D, the manifold dimension. So if I try to embed into too low of a dimension, I'm not going to be able to obtain the structure. I can allow that embedding dimension to be larger. That's okay. And what I want is the Euclidean distance between the embedded points, so phi of mu I minus mu j in Euclidean norm, to be approximately within maybe some small error of the geodesic distance between the two measures in Wasserstein's on the manifold, excuse me. Okay. So this is the goal of my problem. And to illustrate sort of what this could look like in a practical context, so here I have a Swiss roll manifold, and I have a sampling of it, so that's represented by these points on the left-hand side. And I have these 2 points denoted by circles here and here, and the blue arc is the geodesic curve from one point to the other on the Swiss roll. So if I'm a walker on the Swiss roll, that's the path that I would walk to expend the least amount of energy. And in the middle figure, what you see is, so given our sampling of the manifold, we would construct some sort of graph on those samples. So I connect points by vertices by some rule that we'll discuss in a moment. And then the red line is, it's a piecewise linear curve, and it is essentially the graph geodesic, or the graph shortest path connecting these 2 points on my Swiss roll. So the goal of the manifold learning in this case would be, here we have a very simple manifold. We want to sort of flatten the Swiss roll to be this two-dimensional plane in R2 or embedded in R3. And ideally, what we want is, here you see that once we've done the flattening, so you see the graph here on the right-hand side, and there are some holes based on sampling density and how I formed the graph. But we want the distance or the length of the blue curve to be approximately that of the red curve. Okay, so that's the goal. So obviously there are some requirements there. I need the sample densely enough, and I need to form my graph in a nice way in order to achieve this. Okay.
Can I just ask a quick question, Keaton?
Sure.
So I'm assuming, right, so dn isn't the Wasserstein distance itself, but are you kind of assuming that it's kind of connected to the Wasserstein distance, so it's somehow like the geodesic distance which is induced by the Wasserstein distance, or is it kind of completely separate?
Yeah, that's a good question. So I mean, essentially, I have in mind, yes, it should be induced by the Wasserstein metric. And so I would do a construction where, I define a length of the curve between points on the manifold as the supremum of piecewise segments. And I sum up the Wasserstein distance, and then take infimum over curves. So yes, in that way, I am going to assume basically that those geodesics are induced by the ambient Wasserstein metric, which is the same in the Euclidean case. I'm always going to assume that those geodesics are induced by the Euclidean metric. Yeah, thanks. So from that discussion, hopefully it's clear that my notion of distance and my notion of where my data manifold is embedded actually can have a really big effect on my embedding and even what sort of structure I can understand. So here's just a very small example, toy example. Suppose I have these two images and these two disks. Okay. Um, if I treat these as vectors in Euclidean space, which is very common for image processing, uh, I don't really have any information here, right? Because the Euclidean distance between these two is going to just be determined. It's going to be twice the mass of the disk, essentially. Okay. And so if I do that, if I have these 2 points as vectors in Euclidean space and I look at the line segment between them in Euclidean space, if I sample that line segment, I get something like in the top row, right? So I just have these pixel intensities at two different locations. And as I go along the line, I start to dim one of them and increase the intensity on the other. And this could be problematic, for instance, because something on that line segment, like these middle two images, are not in my data space, if my data space is translations of this disk or something. On the other hand, if I had a notion of distance where I literally just move the disk upwards in the figure, then that line segment would be more meaningful to me. And because each of these points, these middle 2 points, are still in my data space. Okay. And so that's one of the main reasons why we want to say, well, rather than using Euclidean distance between images treated as vectors, which somehow obscures the structure and gives me something that may not be meaningful, I'd like something more like the second row here, because somehow that's preserving some salient features of my data. And that's what brings us to Wasserstein distances. So what we're going to do is I'm now going to consider I'm going to give you a very brief overview of Wasserstein distances, which come from the theory of optimal transport. So what we will essentially do is again, thinking of images, we're going to treat our images as probability measures for image data, typically in R2, and I have a figure to illustrate that later on. But in general, we have the space of probability measures on Rn with finite second moments. And now we'll work to define the Wasserstein metric on this space. Okay, so the original formulation, for the original formulation, we'll assume that mu and nu are absolutely continuous for now, but we'll drop this assumption in a moment. And Monge in, I think, the 1700s considered this problem of, so suppose I have these two mounds of dirt, which are my probability density functions here. So this is the density of mu, and this is the density of nu. And, so suppose this is at some construction site, and I have this mound of dirt given by the density of mu, and I want to transform it or shift, manipulate the shape of it to be in this other sort of distribution given by nu, right? And I'm a lazy construction worker, and I want to expend the least amount of energy to move the dirt from one configuration to the other. And so what I ask for is I want to minimize over all possible ways of transporting this dirt from one shape into another. And I want to minimize the amount of effort I expend. And the amount of effort I expend is going to be measured by the distance that I have to transport any sort of infinitesimal bit of dirt and then integrate it over the domain. So So here you see the cost function here. I'm going to integrate of, my t of x, which is where I transport the dirt from the x, the original location, and I'll just do the square Euclidean cost there with respect to the measure of mu. And the requirement here is that the push forward of mu is new, meaning that exactly what this diagram says, I take this mound of dirt and I transform it into this shape. Okay. Now it'll become maybe important in a moment. This T is called a transport map from mu to nu. It doesn't always exist. For example, if mu was a Dirac and nu was a uniform distribution or something, but it's a good example to have in mind. Okay, so the Kantorovich problem is formally stronger than this, but in the case where both of these objective functions have a minimizer, they're equal. So the Kantorovich formulation is I take my two measures and I look at couplings, which are probability measures on the product space. So in this case, Rn cross Rn, such that the marginals, when I restrict to one copy of Rn or the other, give me mu and nu. So that's that notion of coupling. I view from one way and I get nu, the other way I get mu. And then the cost function is the integral of just x minus y squared with respect to this coupling. Okay. And the salient fact for us is that the solution to the Kantorovich problem forms a metric on the space of probability measures with finite second moment. Okay. And so this is what we call the Wasserstein metric. So if I don't take square root on the right-hand side, then this is the square of the Wasserstein metric distance between mu and nu. Okay. And the nice thing about this is, so suppose again, we're in a nice case where I have a transport map. Oh, sorry, I think I didn't say it. The optimal coupling pi here is called a transport plan. Okay. So map is Monge, plan is Kantorovich. So if I have a transport map, I can look at what's called the displacement interpolant between mu and nu. And this corresponds to sort of the line segment or geodesic segment in Wasserstein space, where if I take little t equals 0, I'm starting at mu, and little t equals 1, I'm getting all the way to nu. And so the line segment there follows this trajectory that I showed before. Okay, so that Wasserstein metric is giving us that sort of notion of distance between measures that's useful. And just to show you, this is from a paper by Kaluri et al. This is an example of two different faces from the Yale face database. And the middle three images are the displacement interpolant, or points along the displacement interpolant between the two faces. And you can see, rather than doing pixel-wise distance, I don't have face artifacts or pixel artifacts. I just get a smooth transformation from one face to the other. Okay, so let's talk about how some manifold learning algorithms work. Not everything falls under this category, but these are distance-based ones. So I'm given, again, finite samples of a manifold in Wasserstein space. I will construct a graph. So this could be k nearest neighbor or epsilon neighborhood graph. And the weights between the edges, whichever edges I form in my graph based on that rule, are the square Wasserstein distance between the 2 points. Okay. And then this gives me a distance matrix that's based on the edge weights. So I'll more on that in a moment. It could be exactly the edge weights, or it could be something slightly different. And then my embedding is based on that distance matrix. Okay, so I'll highlight three particular variants of this and show you sort of what the distance matrix is and what the embedding is. So multidimensional scaling, which goes back to, well, originally the theory kind of goes back to the 30s and more developed in the 60s and 70s. In this case, I take k nearest neighbors. I take k equals n. So I actually form a complete graph on the data. And then the weights, the Dij, is just the square Wasserstein distance between the points. And then the embedding is based directly on the spectral decomposition of, I say of D here, but actually a slightly modified version of D. So because I do a complete graph, what that means is MDS is sort of designed to find sort of more flat structures And so that's really what you should have in mind is I have some sort of flat space like this, and then I want to find an embedding. So that's what MDS does. Isomap is the sort of basic nonlinear version of MDS. And here I form my neighborhood graph and I take k less than n or epsilon small, for instance. And then what I do is for every 2 points, my distance matrix value dij is the graph geodesic distance between the two nodes. Okay, so think of that illustration of my Swiss roll from before. And then the embedding is the same as MDS on the graph geodesic matrix. So it essentially corresponds to PCA on a slightly transformed version of the geodesic distance matrix. Okay. And then diffusion maps is a little different. Here I take the graph Laplacian of my neighborhood graph, and then the embedding is based on generalized eigenvectors of D. There's a little more nuance to that, but I don't want to dwell on it. But that essentially is the spirit of diffusion maps. Okay, so there's some parameters that one has to consider there, how to choose the K and epsilon, and then each of these things sort of is designed to find a little bit different structure. So MDS, I said, you're kind of looking for flat structures. Isomap is a really good candidate for things like the Swiss roll that I showed before. So it really will, once you compute those geodesics, you can sort of unfurl it using the same embedding as MDS and get something that is an embedding that's approximately an isometry. So what I'm going to propose for the rest of the talk is a very simple variant of these ideas because those algorithms were originally formulated in Euclidean space. And so I'm going to do the direct analog in Wasserstein space. I'm going to take my measures. I'm going to form the graph on them. I will compute the Wasserstein distance between every square Wasserstein distance between every pair of measures. And then I will either do the graph construction or not. If I don't do the graph construction, then it's really just MDS. And so I have my complete graph. If I do the graph construction, then it's the analog of Isomap. And then in the final embedding, I do the same as the MDS embedding. So really, this is essentially MDS or Isomap using Wasserstein distances between probability measures. Okay, and the MDS variant of this was, as far as I know, first discussed for brain imaging data by this paper by Wang et al. In 2010. Okay. So the assumption here is one thing that I'll discuss for a bit on the next slide. Actually having probability measures as my data is typically not how my data is going to arrive to me. So how do we understand this in a more general setting like imaging data? So suppose that I have vectors in RD for some large D, and for the moment, let's just assume that they're from images. What I'm first going to do is I'm going to sort of create a probability measure out of these. So for images, what I would do, or one way I could do this, is I map my pixel grid down onto a grid in 2 dimensions centered at the origin, typically. And then wherever for every pixel, so for every point on that grid in 2 dimensions, I assign a Dirac where the height is the pixel intensity value for that pixel. Okay, so for instance, for MNIST, I would have a 28 by 28 grid in the unit square, and I would have 28 Diracs or fewer based on 0 locations, and that would be the measure that corresponds to that image. Okay, so here's just 2 examples, and then now that I have these images, I can compute Wasserstein distance between them and then run the embedding. And one of the reasons that this can be sort of better than the Euclidean distance, other than what I've said before, is that in contrast to if I vectorize these images, these measures are keeping spatial information, like where the Diracs are based on the 0 and things like that. So it's keeping more information than if I vectorize these both and consider Euclidean images or Euclidean distances. So there are a few issues that I'll talk about for the remainder of the talk that in order to understand the performance of these embeddings, there are a few things that we have to sort of understand. One difficulty of these is the computation time, for the reason that if I have two measures with, let's say, little n Dirac masses, then computing the Wasserstein distance between two such measures exactly, so computing the Kantorovich plan through a linear program, is complexity about n cubed. And so if I have many samples from my image, so if my resolution of my image is large, that's problematic because I have to now compute capital N squared Wasserstein distances, which are this computational complexity. Okay, so that's typically undesirable, especially if you have large amounts of data. So we'll talk about some ways to mitigate that. And then the other thing that I have to understand is, so back to that Swiss roll analogy, I need to know sort of the geodesic approximation quality. So I do this graph formulation, I make graph geodesics. How well does that capture the manifold geodesics? And then the other thing is, if I'm trying to build a theory, what we're essentially going to start with is assuming we have nice measures, like complete, like absolutely continuous measures in Wasserstein space, understanding how the embedding looks there, and then we need to understand what happens when I go to discretize those measures. So these are, both images here are discretizations of maybe some continuous measure that I could form based on the zero. So the geodesic approximation result is known, and so I'll start with that. So this is a synthesis of results from Bernstein et al. In 2000 and Arias Castro and Lejuic in 2017. So suppose I have a smooth compact manifold, and here the parameter that's going to govern some of the bound is the reach. So that's the supremum of distances away such that from the manifold, such that every point at that distance away has a unique closest point to M. So I'll come back to that when I look at this bound. Suppose I have a delta sampling of the manifold. So that's with respect to the geodesic distance. So any point on my manifold, I have a sample point within geodesic distance delta for that point. And then if I make an epsilon neighborhood graph over those points where epsilon is less than the reach, then I get this equivalence between the graph geodesic distance, which is this one, and the manifold geodesic distance on either side. And the bounds, as you see, what I need here for this to be close to an isometry is here I need epsilon to be small compared to R. And here I need delta to be small compared to epsilon. Okay. So a quick two examples maybe to understand this. If I had a plane, the reach is infinite, and so there the epsilon doesn't matter, which makes sense, right? I can then just take a fully connected graph, and that's going to give me actually geodesics. On the other hand, if I had something that's highly curved like this, the reach is small because points here in the middle may start to have many closest points. And so there you can sort of see I need more sample points like this so that I don't actually accidentally end up jumping the gap on my graph. Okay, so the tighter your manifold is curved, for instance, the finer the sampling needs to be. Okay, and the reach, I believe, is a lower bound for the curvature of the manifold, and so that's kind of, those are similar notions, right? So this is proven for RD, but you can extend these results to the Wasserstein case. So another, when I sort of state some of my main theorems, I want to, in order to understand the embedding quality, the way we're going to view this is as a perturbation of some idealized embedding. And so we're going to use pretty heavily these NDS perturbation bounds, and there are corresponding Isomap perturbation bounds from Arias Castro, Javanmard, and Pelletier. So this is a really nice paper where they consider perturbations of these embeddings. And essentially the way to understand this theorem is as follows. So the y's here, these are going to be points in R little d. So really, these correspond to an idealized MDS embedding of data that I have. So this is ideal MDS embedding. And Z's are going to be actual MDS embedding based on some perturbation of the Euclidean distances of the y. So for the moment, because I'm doing MDS, I'm considering Euclidean distances, but to transform this into isomap guarantees, essentially replace Euclidean distances with geodesic distances. So there you would be considering graph geodesic estimates of the manifold geodesic. Okay, but we'll focus on the Euclidean case for now. So essentially what this says is the lambda i's, these are scalars that are going to be approximations or perturbations of the sort of idealized Euclidean distances for the idealized embedding. And so what I essentially need is the Frobenius norm of the difference of these distance matrices coming from lambda or delta to be small enough. And this pseudo inverse of y term here is essentially a factor that you're stuck with. So they sort of highlight where this comes in and why it's there, but it's something that you basically can't get away from. So if that is small enough, then the bound is, so this is a Procrustes distance here on the left, because MDS is ambiguous up to orthogonal transformation. Because if I have a set of points with a set number of Euclidean distances, I can translate those points, or I can rotate them or undergo orthogonal transformation, and all the pairwise distances are the same. So this is essentially an alignment distance. So I have my idealized embedding y, I have my my perturbed embedding z, and I want to align those as best as possible. So that's the distance on the left. So OD is the orthogonal group on d dimensions. Once I've aligned them, I have that notion of distance, and the upper bound is essentially in terms of the Frobenius norm of the difference of the idealized distances versus the perturbed distances. So we'll come back to this, and I'll give some further explanation there, but this is what we're going to use. Okay, so here's one of the main results I want to present today, and it's based sort of directly off of that. So forgive the color explosion that's about to happen on the screen. It's really, I really am just trying to help you understand which piece corresponds to which, and I haven't yet found a better way to do it. So suppose I have some data measures in W2. You should think of these as perturbations of measures on a manifold. Okay, so those are going to be denoted with blue color. So in orange, I'm going to have my idealized manifold that I'm thinking of my data as coming from. So, and for the moment, to use the MDS perturbation bound, I'm going to assume a very strong assumption that this manifold is actually isometric to Euclidean space, where I take actually the Wasserstein distance between elements of my manifold. So really, this is a flat manifold. I'll talk about how to extend this to manifold geodesics on the next slide. So that means there's some point configuration in RD, and those are the y's. So these are going to be my idealized embeddings, such that the Euclidean distance between the y's is equal to the Wasserstein distance between the elements of my idealized manifold. So what you should think of here is, so I have this simple case, I have nu I, and then I may have like slightly off the manifold is my mu I, and so on. So the mu i's really you should think of as a small perturbation of the nu i's, which are my manifold data. Okay, so orange is the manifold. And now I have some approximation of the Wasserstein distance between mu I and mu j, again, for the reason that I don't necessarily want to spend the full computation cost to compute the exact Wasserstein distance between mu I and mu j. So these lambda i's can cover things like discretization effects, graph geodesic estimates of manifold geodesics, or other artifacts, okay? And then the teal color here, these are going to be, so Zi is going to be in R, so this is going to be in R little d. So these are going to be the embedding points based on the lambdas, which are the estimates of my actual Wasserstein distance. Okay. So I'm going to just give names to how far I perturb the manifold data, as that's tau 1. So this is square Wasserstein distance between the actual measures that I observe, mu I and mu j, and then this is the Wasserstein distance between the points on the manifold that I'm sort of expecting to observe. And suppose that's no larger than tau 1, so this is just the maximum maybe of over my sample set. And then tau 2 is going to be the quantity that governs how good of an approximation I made to the Wasserstein distance between my actual data measures. So here, the only thing I really compute are the lambda ij's. Everything else I'm assuming is just there, but I don't actually compute it if I go to do the algorithm. Okay, so as long as these quantities are sort of small enough, and this can be you see can be a fairly strict assumption. There are some ways to make it a little bit more relaxed, but essentially you do need both of those things to be small. Then the output of the ZIs, which are the output of MDS on my approximated Wasserstein distances, are Procrustes distance away from the idealized embedding. If I had all the exact Wasserstein distances, and the upper bound is this term here. So really the key piece here is that quantity tau 1 and tau 2, which again, so how far the data is away from a subset of Wasserstein space that looks Euclidean, that's what tau 1 is. And then tau 2 is how well I estimated Wasserstein distance. So for instance, one way to estimate Wasserstein distances is by entropic regularization. So this is from Couturi. And that's a fast approximation to a single Wasserstein distance. Another way to do it that I'll talk about shortly is linearized optimal transport.
So Keaton, can you just remind me what is Y dagger?
Oh, sorry. More Penrose pseudo inverse of the matrix Y.
Okay, thanks.
Yeah. And that is a spectral norm there. Okay, so this is kind of the main first results. I won't state rigorously the extension to geodesic distances, but let me just say, so suppose I have something like the Swiss roll in Wasserstein space. So then the key feature of the Swiss roll really is that the manifold geodesics can be realized by Euclidean geodesics, right? I just unfurl the Swiss roll, and then I have Euclidean distances between line segments, right? So there, essentially that second quantity, tau 2, is going to measure how well the geodesics are approximated by the graph geodesics. And it's also going to capture how well the Wasserstein distances on the segments, the graph segments, are approximated by whatever method you use to approximate. So there you could essentially split it into two terms based on each of those factors. Okay, and then you can state a very similar embedding guarantee from there. As a quick aside, there are cases that are very simple where that first measure tau 1 is 0. So that means that you have a flat manifold in Wasserstein space that is isometric to Euclidean space. So very simple submanifolds that look like that are take a fixed measure, translate it around. This is isometric to Euclidean space for the reason that the distance between two such measures is the Euclidean distance between the translation vectors. You can also show this for dilations of a fixed measure. If I dilate along coordinate axes, then that's also isometric to Euclidean space. So those are very super simple manifolds, but in those, you only have to worry about the geodesic approximations. Okay. So in my last maybe 10 minutes or so, I will just give one inclination or one method to speed up the computations here. If you like to use entropic regularization, that is one way to do it, but I'm going to talk about using linearized optimal transport in order to do it. So linearized optimal transport works as following. So essentially here, I'm going to replace Wasserstein distance by a Hilbert space distance. And what I'm going to do is I'm going to fix some reference measure. There are different ways to do this. It could be sort of arbitrary, or it could be maybe a barycenter coming from my different data measures that I actually observe. And then what I do is, so I have this reference measure sigma, and then I have some of my data measures like mu1, mu2, mu3, and I compute optimal transport maps from sigma to mu1, mu2, mu3. Okay. And then what I do is, this would be T sigma mu1. So that's the transport map in the Monge sense from sigma, which is the reference, to mu1. And then these are functions in L2 of sigma. So sigma here is the weight for this L2 space. And I just define the LOT distance between mu and nu with reference sigma to be the L2 of sigma norm between the transport maps. So I'm comparing, for instance, this transport map with this one, and this corresponds to embedding. So I map mu into T sigma mu, and this embeds Wasserstein space into L2 sigma. Okay, so I'm embedding W2 into Hilbert space, where I have a lot of nice structure in theory to help me do a lot of things better or understand them more easily. Now, another way to view this, what it corresponds to, is essentially, so this L2 sigma is the tangent space to Wasserstein space at the reference sigma. Okay, and so what I'm essentially asking for is, so I have these mu and nu down here in the Wasserstein space. I have some curved geodesic between them maybe, but I lift all of that up to this tangent space and compute the distance there. So if the tangent space is close to Wasserstein space, then my LOT distance is close to the Wasserstein distance. Of course, at a highly curved part of Wasserstein space, this may not be true. And so part of that is finding a good reference to hopefully make these distances a good approximation. So that's the LOT distance briefly. In our work, we're actually, because we're not going to assume everything is absolutely continuous, we're going to have this sort of empirical LOT distance. And essentially what this means is we're going to assume we have an empirical sample from mu given by mu hat here. So I sample IID from mu and take the average. And I'm going to have the same empirical sample from nu and also from the reference sigma. And then I'm going to look at a discretized version of this L2 integral, and that's going to be what I call the empirical LOT distance. So we'll compute this actually in multiple stages, and so I'll highlight that here. If I want to understand the distance between, or the difference between Wasserstein distance between mu and nu and this empirical distance, I do it in multiple approximation steps. So the first is just how far away the LOT distance is from the Wasserstein distance. Okay, so that's that picture I had on the previous slide. The second term is just the discretization error between mu and nu. So here I have LOT distance when I take the transport maps from sigma to mu and nu, where these may be absolutely continuous, versus the LOT distance between the empirical measures that I get from sampling mu and nu. So these are the things that I actually observe, mu hat and nu hat. Then, because this assumes that sigma is absolutely continuous. So then I have to take into account that discretization effect. So that's going to get us to this empirical error where I approximate this integral by essentially like a Monte Carlo integral estimate. Okay. And so that is discretizing sigma. Okay. And we can, the point essentially is that we can bound each one of these terms separately from some existing results in the literature. And so this is my last real result that I'll say. So suppose now my data comes from deformations of some absolutely continuous measure mu by some set number of deformations. So you can think of these as the like the translations, but something I can parameterize easily. And so under certain structural assumptions, I don't have too much time to get into these, but there's essentially, we'll assume this compatibility condition, which more or less means that the LOT distance, it's one way of saying the LOT distance is a good approximation to Wasserstein distance, essentially saying if I go from sigma to mu, and then mu gets pushed forward to some other measure based on one of my deformations, then if I look at the transport map that gets me from sigma here, it's approximately the same as taking the transport map to mu and then composing with the deformation that gets me to this new point here. So that needs to be small in the L2. The other technical assumptions, so the transport maps need to be uniformly Lipschitz. And the key features in our bound are going to be the sample size for mu I, and then the sample size, which is k, the sample size m for sigma, plus some other regularity assumptions. Then the bound is that with probability at least 1 minus delta, the Procrustes distance between the actual embedding and the idealized embedding is bounded above by, so these are all the same terms as before. And then this term in parenthesis is the estimate of based on the estimate of the Wasserstein distance. So I have this epsilon to some term that depends on the number of moments I have and the dimension of my measure. And epsilon is the compatibility. So that's again how close LOT distance is. The second term is I've written it abstractly as some function of k, the sample size of the mu i's. And this goes to 0 at a rate that is known, which depends on whether you're using the linear program or Sinkhorn to approximate Wasserstein distances between the discrete distributions. And then this term is in terms of the success probability that you want and the number of samples you take of the reference distribution sigma. Okay, so again, here in words, it's compatibility error, so LOT error, discretization error based on mu I, and discretization error based on sigma. And these are built on a number of existing results in the literature by these authors here for each of these terms. Okay. And just briefly, you can translate this to a non-compact measure. So here I assumed compactly supported measures. You don't have to, you just require tail decay and then a couple other regularity assumptions, and the argument goes through. So I won't have time to talk. There's some computational issues basically between the discrete measures. I compute first a Kantorovich plan, and then I make that into a transport map by barycentric projection. But in the end, the upshot is that's a much more computationally feasible method for doing these embeddings than just computing all the raw Wasserstein distances. So in my last minute or so, I'll just highlight some experiments here. So here's a simple case where I have a translation of a unit disk, and each of these points that you see on the top are the centers of the translation. So my disk starts maybe in the center, and then I just center it at these different points. The non-convexity of the translation grid here is something that affects things when you start to do geodesic distances. If I just do MDS embedding based on Wasserstein distances, we recover the parameter set more or less exactly. And then the bottom row is just showing some standard. If I treated this image as a Euclidean vector and use some standard embeddings like Isomap, MDS, diffusion maps with Euclidean distances, I get this squeezing in the middle because of that gap in the translation set. So this is just arguing for the fact that using Wasserstein distances is giving some better structure or better understanding of the structure in the embedding than using Euclidean distances. Okay. And then here's a maybe slightly more advanced experiment where we took a few images from MNIST of different digits and did some different embeddings. So these use the geodesic computation step. So the top left and middle are the Wassermap embedding using Wasserstein distances. Everything else here uses Euclidean distances. And kind of the point here is that I find kind of some slightly better separation using Wasserstein distances than, say, here's the equivalent Isomap with Euclidean distances. I do okay on some things, but they're a lot more, the classes are a lot more intermixed than they are in the Wasserstein embedding. Okay. And just very briefly, here's a finite sample version. The embeddings all look fairly nice. There's some sampling density issues that you can run into for the quality of the embedding, but overall, even with the linearized optimal transport case, with modest computation costs, you're still recovering a lot of the structure of the parameter set. And here's just a short evidence where the timing for these two are LOT embeddings using Sinkhorn or even the linear program to compute Wasserstein distances. And this is the red here is Wassermap, where I just compute all of the Wasserstein distances together. So the linearized optimal transport really does save you quite a bit on the computation time. Okay. And very brief summary. So we explored distance-based methods for manifold learning, and this notion of treating particularly image data, but you can extrapolate it to other data sets as probability measures, somehow is finding more structure, low dimensional structure from the data in a better way. And our sort of main results I presented were perturbation estimates for submanifolds of Wasserstein space. And in the future, we'd like to understand sort of task performance, whether I'm doing classification or clustering after performing such embeddings, other ways of speeding up the computation, and then definitely more exotic submanifolds of Wasserstein space than these sort of flat or Swiss roll type manifolds. So just to sort of throw it out there, one preliminary result in this vein is a paper with Caroline Moosmuller, Bernard Schmitzer, and Matt Thorpe that you can find on arXiv. So thanks.
Hey, thank you very much, Keaton. Right, I will just stop the recording, and then if there are any questions, please either put them in the chat or feel free to unmute yourself.